Thank you. Thanks to the organizers for having me here. So I'll be talking about the distribution of cold gas. By cold gas, I mean just H1 or atomic neutral hydrogen in the local universe. And what we want to do is try to find, using observations, try to see how we can distribute them in halos, and also try and distribute other properties of halos or galaxies tied up and tie them up with cold gas. So this is something I've been working with my PhD student and former postdoc. She's now in NCRA, an undergrad and a current student. So just a brief history of neutral hydrogen. We have seen some form of this earlier in the talks. So post recombination, the universe is mostly neutral. Then you have the first stars, first galaxies, and by the end of, by the time you reach redshift 6, the universe is mostly ionized. And then there are trace amounts of neutral hydrogen which are able to self-shield themselves from the ionizing radiation, and these are found in galaxies. So most of the amount of atomic hydrogen that you see is in galaxies. So it's a good tracer for galaxies in the post reionization era. And so you can do cosmology, large scale structure, and see using 21 centimeter. But also in terms of understanding how galaxies obtain H1, how it's recycled into stars, feedback, this whole cycle, that itself is an important question. Okay. So coming from a theory background, ideally I would want to get all of this. So this is just an illustration of the Whirlpool galaxy in radio, IR, optical, UV, and X-ray. Probably there's some AGN sitting here, which is heating up the surrounding medium there. Okay. And I don't want to try and reproduce this, but rather try and reproduce these kind of galaxies in a statistical sense. So I want to get distributions or multi-wavelength distributions or mass functions, luminosity functions, not marginalized individually. Okay. So multivariate functions. So since we are talking about quasars, I think one of the things which quasars do is they grow rapidly. So this is from a large hydrodynamical simulation, which was trying to reproduce redshift 6 quasars. So what's plotted is the accretion rate, which is a proxy for the bolometric luminosity of the quasar, that's a black, as a function of redshift. And this is the star formation rate of the host galaxy. And you see that you are able to get them. This is the detection limit of SDSS. So you are able to get the right numbers in hydrodynamical simulations. Only thing is that you need a very large volume, and they grow exponentially. Then they hit peak phase, and they self-regulate themselves and the host galaxy. So the star formation rate falls by nearly an order of magnitude in a small time scale. And since star formation rate is related to the amount of cold gas that you have, you expect also, obviously, that these kind of feedback processes or heating processes, AGN is one of them, to destroy the amount of H1 or H2. Okay. So just as a brief aside, so this is what we have as the stellar mass function. And this is what you would expect to be the stellar mass function at maximum efficiency. By maximum efficiency, I mean all the baryons are converted from the halo mass function or with the baryonic fraction into stars. And the shapes are quite different. So obviously there are some astrophysical processes which are regulating the shape of the stellar mass function. So you expect supernova feedback to suppress this end, the low mass end, and you expect AGN feedback to suppress the high mass end. So going back to observations, we talked about star formation rate. So this is just one typical galaxy. There are a bunch of them in this paper. So you see, we'll just focus on the atomic gas. This is the molecular gas, and this is the total star formation rate. And you see there's a strong correlation between the molecular gas and the total star formation from region to region. Whereas with atomic gas, it's not as strongly correlated. Another galaxy, something similar. So what we expect is that the molecular gas is forming from the amount of atomic gas in these denser regions. They're able to cool and then eventually collapse and form stars. So the atomic gas is responsible eventually, or is a reservoir for of cold gas, which will eventually turn into stars. This is something which we know as the Kennicutt-Schmidt law. On cosmological scales, we can look at the cosmic star formation rate density as a function of redshift. And there is a peak at around redshift of 2 to 3. And then it drops by an order of magnitude from redshift 2 to 0. And do we see the same kind of thing in H1 gas? Before that, we can integrate this quantity, okay, and we'll get the the stellar mass density as a function of redshift. So that's the black line if I integrate the star formation rate over redshift. And these are separate observations which are able to probe the stellar mass in surveys. That's by just computing what is the stellar mass function and then taking the first moment and integrating out. So the next question is, since H1 and star formation rate are tied, what is the decline from redshift 2 to redshift 0? There is pretty much no decline. Okay. So we need to understand this whole process of recycling and what is the time scales involved in of halos in accreting gas, converting it to stars, and depleting the reservoir and accreting again fresh supplies of gas or cooling in situ there in halos. So that's not very well understood. So that's something which we want to understand also. So what we'll do next is to look at the ALFALFA survey. This is an old data set, which is 40% of the data. Towards the end, we'll go to the 100% data. And that will have probably 3 times to 3.5 times more galaxies here. So after putting relevant cuts, so it goes out to redshift 0.05. You start out with 10,000 galaxies. This is the array and declination of the alpha-alpha galaxies. The red patch is overlap with SDSS. And then once you put some cuts due to RFI, etc., you're left with around 8,300 galaxies. And this is the flux as a function of W50. Okay. So these are the detected objects, the histogram of that. And you see that unlike an optical survey, there is a dependence on the width of the line. And that comes due to the, since it's a line emission, face-on galaxy is more probable to be seen as compared to an edge-on galaxy at a fixed level of noise. So when one wants to find out the mass function, it's not just a flux limit. It is a flux limit which is dependent on the velocity width. So you have to first estimate a bivariate mass velocity function, and then you integrate out over one or the other to get either the mass function or the velocity width function. So this is an addition, and you get it for free. Basically, it'll tell you it's related to the rotational velocities of these galaxies, although you don't measure rotational velocities. So this was applied by, I think it was done in the context of optical survey in gamma. So you have 5 bands, but you want to get a luminosity function. Let's say you start with SDSS R band, and you want to get a luminosity function in U band, but your selection is in R band. Then you have to do these kind of things to get the U band luminosity function. So this is one patch of alpha-alpha. Red and blue are red and blue galaxies. So you, sorry, this is in SDSS. When you go to alpha-alpha, very few of them. Okay. So this is in terms of the redshift and I think RA. Okay. Now the same sample or the same volume, you look at SDSS and you see this is in terms of color and magnitude. Again, alpha-alpha, you also have color and magnitude. It turns out that 98% of the H1 selected galaxies have optical counterparts, but the reverse is not true. Okay? So you, out of, let's say, 10,000 galaxies in the red, this demarcates red and blue. you get only 10% here of detections and only 30% detections here. And this looks okay because H1 is associated with star-forming galaxies. So you do see more detections in the blue cloud. But this is not a small non-trivial fraction, and one has to worry about that. So once you do that, you use this, try and estimate the selection function based on the data itself. And what has been plotted is the individual detections in the width and mass plane. And this is the 2D mass velocity function. You integrate out over velocity, you get the mass function. You integrate out over the velocity, you get the velocity width function. You can play this game for red and blue galaxies, and you see that the total is black, then you have blue and red. So the total is basically dominated by blue galaxies, or the full mass function is basically driven by the blue galaxies, but the high mass end is actually dominated by the red galaxies. So here red means that they're not intrinsically red. We have not corrected for dust or inclination effects, etc. So this is what we just see in the observation. So this is the velocity function. And let's forget about these other points. This is just comparing with previous observations. We'll look at the solid points. And again, you see, like what you see in a galaxy survey for the stellar mass function, you see something like a bimodal distribution, but it's not very obvious in the shape of the total velocity width function or the mass function. You can extend this game further. You put cuts in color and magnitude and get conditional mass functions. Since I won't show you the conditional mass functions, but rather get you what is the dependence of omega H1 on color and magnitude. So we put cuts. The reason we put cuts and not to do it in bins is because we have very few galaxies. We take these cumulants and then differentiate. So you do that, and this is the omega H1 distribution in the color magnitude plane. So the bulk of omega H1 comes from the blue cloud, but there is around 20% of omega H1 coming from the red cloud. So when you do stacking or targeted surveys, it's often based on targeting star-forming blue galaxies, but in that case, you are going to miss out a few of them in the red cloud. So now that we have looked at just the H1 distribution, we can go ahead and start looking at, can we extend this to halo, to finding out how they're related to halos. But as we discussed, not all galaxies have H1 detections above the limit. And this situation is more severe for redder galaxies. And on average, red galaxies, luminous red galaxies are associated with more massive halos. So you don't expect a monotonic relation between H1 mass and halo mass. And this has been seen in a bunch of surveys which have targeted H1 in by stellar mass. So you have surveys like GAS, and then you have surveys like Atlas 3D, which have tried to look at H1 in red galaxies and stellar mass selected surveys. And the relation is not monotonic. It actually, you have less H1, or you have mostly no detections in red galaxies. So what we want to ask is, can we apply techniques like abundance matching to H1? The answer is no. So we have to find a way to, if we still want to use that, find a way to do that. And for that, what we want to see is there a correlation between stellar mass and H1 mass for an H1 selected sample? And the answer is yes. I have not put that plot, unfortunately, here, but the answer is yes. Okay. So there is a monotonic relation between stellar mass, and stellar mass has a monotonic relation between with halo mass. So for an H1 selected survey, we should expect a monotonic relation between H1 mass and halo mass. So for that, we have to define an H1 selected halo mass function. So how do we do that? So what the alfalfa people with Guo, I think Hong Guo, they have done is taken the alfalfa data cube, looked at it in SDSS, and stacked all detections, and mostly in the higher masses, stacked all the H1 detections based on their optical counterparts. And what is plotted here is the average H1 mass in as a function of halo mass. So you start off with one halo mass function. Here, this is from the MDPL or SMDPL simulation. And you ask the question that how do I get this observation by constructing a H1 selected halo mass function so that the average relation is reproduced. So if I did abundance matching with the full halo mass function, I get the following. If I did abundance matching with the H1 selected halo mass function, I get the following. If I take the average over this, over all the halos, I get this dashed line. This is what I have constructed. So the reason why there's a shift here is that because you are associating all the H1 in a smaller number of halos, so the average content of H1 in a smaller number of halos is larger at fixed halo mass. So this is what you get. So this is the H1 selected halo mass function. It's based on 3 parameters, a constant fraction, a cutoff mass scale, where things get suppressed further. And again, just motivated from the fact that we don't want too much H1 in very massive halos. So just a consistency check, and this is a scaling relation that you get of the H1 mass with the halo mass. So this is the alfalfa data. You have taken the stellar mass and converted to halo mass. And this is based on the H1 selected halo mass function. This is the full halo mass function. And obviously what this tells us is that although we have not calibrated it to this data, this is our prediction, the scaling relation. So obviously one should not be using the full halo mass function to do things like abundance matching. And this is a better description of the data. Obviously the data has scatter, and this is 0.2 dex, so we want to introduce scatter in that. And we do that, and one has to solve it iteratively. On the left-hand side, you have the H1 mass function, which you have. On the right-hand side, you have the H1 selected halo mass function, and this has to be convolved with a function which has the mean H1 mass halo mass relation given a scatter sigma. So we assume this form, a Gaussian scatter, and you fix the scatter and iteratively solve for this to get the mean relation. When you do that, so this is with 0.15 dex scatter, this is with 0.2 dex scatter, and when you do that, the average relation drops. Okay, and what scatter does is that if I'm looking at some rare object, let's say 10.5, it would be associated with 10 to the 14 halo mass, which I don't want. Okay. Now it's less likely to have a 10 to the 10.7 to be associated with 10 to the 14. Likely there will be with 10 to the 13 or somewhere around 10 to the 12.5. You increase the scatter, the mass scale shifts. So the rare H1 objects are now associated naturally with more massive halos, which is what we want. There is no physics in this. This is just doing scatter, and we're trying to get these halos out of the H1 catalog. So you do that, and as you increase scatter, the mean relation keeps on dropping. You can ask, why are we not going to match this mean relation? It turns out that the observed mean relation is an upper bound. So we are free to bring it down further. The second prediction is clustering. So once we have in our mock catalog H1, we can predict clustering. And the red line is the dark matter correlation function. This is projected. And as a function of H1 cuts, the blue are the data which have been measured. And the gray band is what we are trying to predict. We can see the large scale clustering is pretty well reproduced. This is with the zero scatter case. And if you increase scatter, it does a slightly better job. Okay. But the clustering amplitude slightly drops, still within error bars, it's good. So now the main discrepancies are at lower masses. And the reason is that we have made no effort to have assign H1 depending on whether it's a central or satellite. So that needs improvement. Okay. Once this is done, so just two predictions. So basically it's a halo model. But unlike the standard halo model, it's not calibrated on clustering or it's not calibrated on a scaling relation. We have, and it's a 3-parameter halo model if you want, and it's just calibrated on a stacked result. So you can look at correlations of H1. So this is IR, cross correlation between H1 and halos, and autocorrelation of halos. So I've put two cuts, one in halo mass of 10 to the 12 and H1 mass of 10 to the 10.2. And you see, if you go back to the previous plot where I was showing the H1 and halo mass, these are the typical numbers for 10 to the 10.2 galaxies. So their correlation amplitude is pretty much the same. This is in real space, this is in redshift space. And if I want to increase the signal, I just correlate it with higher mass halos, and the amplitude increases. So that may be one way of detecting H1 by or the clustering of H1 by correlating it with larger mass halos. So this is in real space. This is the two-dimensional correlation function. So mass cut of 9.6 and halo mass cut of 10 to the 12. This is in real space. This is in redshift space. This is halo, H1, and cross. Okay. Again, if I go back with the previous slide, there's a slight increase in amplitude of the clustering. So again, I have increased now just the H1 mass cut. Now what I do is increase the halo mass cut, and you can see that the amplitude has slightly increased just by cross correlating it with larger mass halos. This is in real space and this is in redshift space. Again, increase the H1 mass cut. It becomes noisier because there are fewer objects. But again, you are able to look at these kind of things in a catalog. Of course, you have cosmology information at large scales. The interesting part will be actually doing this in observations and trying to see whether even these kind of predictions in 2D are reproduced. So this is still very preliminary, and the one halo term will be interesting to see the environment of H1. So just to summarize, so we have a H1 mass halo mass scaling relation, and you want to compare it with the H1 mass stellar mass scaling relation. And you see that this is from, I think, Moster or Beruzi, one of them. And this is the ratio as a function of halo mass. So around 1 dex lower. And the way I would want to think about it is that heating processes like virial heating or feedback is able to suppress H1 much before or on time scales much smaller as compared to star formation. So the galaxy is still able to produce stars for a while before it gets suppressed in terms of star formation. And that may be because star formation happens in more clumpier regions, whereas H1 is more diffuse. So this is what we get around 10 to the 11. And recently, when I was at IUCAA in February, Saugat was presenting absorber data. And this is what you get in Lyman alpha absorption. And again, around 10 to the 11 is where they see the peak. So two different kind of observations, one in emission, one in absorption. Numbers are not exactly the same. The features are also across redshifts, across virial radii, but we are still getting something similar. And again, this is the Moster relation. So we have H1 and halos. We can quickly go over H1 and stellar mass, but this is like cheating. So we'll quickly go through that, and this might be related to actually cross-correlating with an observational catalog. I can do it in terms of luminosity also. So again, just putting different mass cuts in stellar mass and cross-correlating H1 with stellar mass, and this is what you get. Okay, so to avoid cheating, maybe we should just go and look at the stellar mass function of H1 selected galaxies. And this is just something which came in yesterday by Tanya. So what is shown here is the stellar mass function of in the 100% catalog. This is the H1 mass function. And again, things are shifted. The shift is much larger here as compared to. So I'll stop here and.
Question by Hansen.
Yeah, thanks for the nice talk. There's these new results by Choudhury and other people at GMRT who are looking at
Yes.
H1, and there's also MIGHTY, which is, I think, close to the redshifts you are. So do you have any comments on that? Because we all thought H1 is just an intermediary, and these results seem to think that, okay, maybe it's used in the process of star formation, which is.
Yes, so they have some time scale arguments of, I think you have to deplete them many times. From redshift 1 to redshift 0. So I think those are, so the stacking results and its results are fine. Interpretation, again, I doubt, because we are showing that if you select a sample, it's always biased. So they have targeted, I think there was one intermediate stacking result at redshift 0.3, 0.4, and that I'm not very clear about, because it's based on a B-band selected survey. So you are going to miss out something. So you cannot, you can put a bound, a lower bound on omega H1, but I won't convert it as a constraint on omega H1 at that redshift.
Okay, more questions? Shadab?
I was curious about the clustering plot you showed. So you mentioned that at small scale, there's something you can do with the satellite which will help.
Right. We have not made any effort.
Right. I was wondering if you can elaborate what kind of things you could try. And another thing I wanted to ask is, why does your smallest scale stop at 0.1? What is driving that? 0.1?
These guys have stopped at small 0.1. So we have also stopped at 0.1, just to make the comparison.
Okay, but you could measure to a smaller
could, in principle, look at even smaller scale.
And also in the data, you
that is, but it goes into the galactic scale, right? So 0.1 is 100 kiloparsecs. So that's about the H1. That's where the rotation curves are. I'm not sure. Yeah.
And could you elaborate on what kind of thing you could try?
So we can put a different fraction of H1, and we'll have to play with those functional forms based on central or satellite. So here, this, I'm assuming this applies to all halos. By halos, I mean central or satellites. I'm not distinguishing between them, but I can have in principle a different functional form. And the part which worries me is this upturn, even at higher mass cuts. So these are very gas-rich systems, and I need to have in the one halo term within 200 parsecs, 300 parsecs, 2 gas-rich systems on average. That part is going to worry me, but so I'll have to think about it. So this upturn, I'm not sure how to deal with.
Okay, my final question.
I mean, we are going to do the weak lensing anyway.
Yes. So just so the other thing which I have not mentioned is I've given Surhud the H1 catalog. We should hopefully get different mass estimates for halo masses.
Yeah, but so I wanted to ask, so these Guo et al. Results that you are using, so they come from?
This comes from some value-added catalog, the halo masses, if that's what you're asking.
Yeah. And so they are using consistent cosmology compared to what you are doing? Or otherwise that changes and shifts the halo masses?
It's around 0.3, 0.7. So what we are using is 0.3 and, oh, sorry, we are using, sorry. Oh, I've not put the cosmology here. So this is the Planck 15 cosmology.
Planck.
I think we are using actually the same cosmology because they also use the MDPL2 cosmology.
That's fine.
I think that is fine. Yeah.
Okay, well, thank you. Let's thanks the speaker again.